All right, folks, let's get started. So today is just a review. I got a lot of stuff here, but it's all stuff you should have seen already. So let's get started. So remember the whole purpose, well, the whole purpose of the 324 and 325, not the main purpose, but the subtle side purpose is get you ready to take the FE. And since it's a requirement for all our EET students to take the FE, great, let's get you prepped. But in a sneaky, subtle way, we are giving you a lot of really good analysis information that hopefully as you go in your careers and you figure things out, you'll actually be able to do a lot of these, I won't say more advanced techniques per se, but at least be able to see where a more generic approach to solving problems for electrical, mechanical, any type of system will hopefully get you some pretty good results. So we kept using Laplace, right? That was the whole purpose of 325 was to live in the Laplace domain. So why is that? Because living in the real world means we have to do and solve differential equations. So we're just going ahead and modeling systems, and we're trying to model them if we can. We would like to model them in the Laplace domain. Sometimes we have to write differential equations and model them in the time domain, and then just convert them to the Laplace domain. Pretty easy. So we started out by coming up with answers, the answers that we wanted, but we actually had to take those back into the time domain, was what we learned in 324. In 325, we actually spend most of our time there. So we have to be able to do that. We have to make sure we have a good background. And so that's what the start of the semester is, converting differential equations to the Laplace domain, using tables and mathematical properties of Laplace to go back into the time domain. And that was really important to be able to do partial fraction expansion, to be able to go back into the, time domain. Then we moved on to transform analysis, because many real world systems, you don't actually know what the input stimulus is going to be. So you come up with a model of a system, and that model of a system will give you an output given any input that you want, as long as you are not exceeding the capability of that particular system, then you can go ahead and do that. And we often did that for electrical circuits using just our transform analysis, and we like to use op-amps. And so if you remember, we did a lot of stuff with op-amps, and op-amps allowed us to come up with easy transfer functions when we did negative RF over RI. If that was a resistive circuit, if we had some capacitors or inductors, now we had to introduce the concept of the Laplace transform, S, in there. And so instead of talking about resistors, then we went to impedances, because we can be very generic. And so impedances apply for DC circuits or AC circuits. That's the really nice thing about Laplace. So we kind of generalized and call them Z's. So go ahead, calculate your gain of your system, calculate your Laplace transform of the system, and then you can calculate whatever values you need. The last thing here is we looked at poles and zeros to define the stability of the system and the response of the system. And if you recall, we really wanted to make sure we hammered the concept of poles and zeros, because we started to do things looking for like root locus and Bode plots, where we did more advanced analysis of systems, where we could design things. We really emphasized the concept of poles, and zeros. So differential equation transfer function, that's the easiest. Somebody or somebody's had written a differential equation to describe the system, of the operation of a system. So we can take that differential equation and bring it to the Laplace domain, and then we can find our transform analysis. In most cases, we neglected any initial conditions. And the reason why we neglected them is because if we included them, it really doesn't skew our results, or if we excluded them, we really didn't get our results all that far off. So, and it's much, much easier to define and work with systems that have no initial conditions. So our results weren't too far off. So let's assume that there are no initial conditions, make things very easy. Then we also looked at writing block diagrams, where if we wanted to find the position or the configuration or the state of any particular system, we could go ahead and do things with block diagrams. And so sometimes block diagrams are better because if you're trying to represent a physical system, you can actually break that physical system up into smaller parts, which correspond to the blocks. So if something is not coming out the way you can expect it, you can actually model those individual points and compare those to each point on a block diagram. And hey, there's a problem between this point and this point. So it really, really, really helps with troubleshooting. We kind of went through Laplace domain modeling of electrical circuits again. We'll do this quickly because we did it last semester. At this point, you should be almost pros in coming up with these circuits, right? Capacitors become 1 over SC, which jives really well with the concept of reactance for capacitors. Inductors is S times L. Again, matching what we would expect for reactances with inductors for AC circuits. And then resistors, there's no change in the Laplace domain for a resistor, which exactly matches, again, the concept of AC circuits with reactance. We don't do anything. A resistor is a resistor is a resistor. And if you go back to the idea of a property, right, we take the current through a resistor, we can get the voltage just by multiplying that current by that resistance. That's a mathematical property. V equals R times I, which is the same thing in the Laplace domain or the time domain. Over here, the voltage across an inductor is L di dt. So we're taking the derivative of the current. We're not just multiplying by the inductance. We also have to take the derivative of it, which means we have to do another different mathematical property. That's why it looks a little bit different there. Once you've converted everything to the Laplace domain, every circuit analysis every circuit analysis calculation approach is exactly the same. There is no difference. And so converting things to the Laplace domain really makes things quite a bit easier. Then we moved on to mechanical systems. I encourage you to understand that. Wink, wink, nudge, nudge. Because these are pretty helpful to understanding a different world, right? We're electrical engineers, but we don't live exclusively in the electrical world. We actually have to be able to, drive a car, right? There's a mechanical system, or ride a bike, or do whatever you need to do. And so being able to compare different disciplines to electrical hopefully makes things, makes you help things a little more understandable. So we have our spring mass damper for mechanical systems. There are different ones, but we can simplify or start off with here. And so we're doing things in terms of force now. So that's the energy in a mechanical system, at least in this translational system. So force is mass times acceleration, or the second derivative of position. And we can write that in the Laplace domain as ms squared times its position. If we have a damper is only going to provide an opposing force when you actually have movement, right? Because it's forcing oil through those ports. So the fact of the matter is a damper is just providing force when you have movement. Movement is velocity. So the first derivative of velocity, first derivative of position is velocity. So the force that's developed because of a damper is B, whatever the damper coefficient is, times S x sub S in the Laplace domain. And a spring is only going to provide an opposing force based on how much you compress or elongate the spring. So that's directly proportional to the amount of the spring constant times the compression or elongation of the spring. Again, that's just position. So we have no derivatives there. That's just direct. Now, all these are simplified because they're all assuming linear operation, but this class doesn't cover any nonlinear stuff. It makes it too difficult. But yeah, and so to do all these problems, you just do force balance. Force balance about an operating point. So pick a point, figure out the directions of the forces, sum them, right, including directions, because now we have to be mindful that things may not be going all in one direction. They can go in different directions. And then you should be able to do transfer functions for whatever. Then we moved on to translational, and they're very rotational, sorry, not translational. And it's the same concept, except now we're talking about torque. So torque developed from something that you have to rotate, or the moment of inertia, is J S squared times theta, because it's the J times acceleration. As you accelerate things, you have to put more energy into the system. Damper is movement, so that's the first derivative of position. So S times theta S times the damping coefficient. And then Hooke's law, which again is just a spring. Kind of harder to see a little bit of a rotational spring. But if we can envision that there is a spring that as you put a rotational thing on it, it actually develops an opposing force. And again, that's just based or rotated or calculated based on its spring position. And it doesn't always have to be rotated this way. You can compress a spring to provide an opposing force. And it's the same thing. Do sort of a force balance, but now it's called a torque balance. And you can do your calculations. These two concepts, we also evaluated a little bit, not a lot, but a little bit, where we looked at multi-input and multi-output systems when we talked about the concept of state space and using matrices to go ahead and do that. That's the more advanced, that's called modern control systems. And you can really get a lot of information out of it. It just takes a lot of work to set things up, but super duper useful. And then we had an example, a mechanical example, where we figured out how to connect or translate between the electrical world and the mechanical world. So we have a transfer function of omega S, which is rotational speed, divided by input voltage. So you apply an input voltage, which electrical engineers are fine with, and we get a corresponding speed out. And we've developed this equation here. I'm not expecting you to develop this equation. You have all the terms and coefficients here, and they're all spelled out over here. So we don't need to get in all those specific ones, but this is a pretty good one to go ahead and start to expand our knowledge of electrical systems and how we can control mechanical systems. Pole zero maps, kept looking back at that, and I don't know if you figured out why we kept looking back at it, but again, when we looked at root locus in particular, it was really useful to figure out what our pole zero maps were telling us. So we kept going back to pole zero maps. We did it multiple times in the semester and even a little bit last semester, because it really does tell you a lot of information about the operation of a system. And so we talked about left-hand half plane, right-hand half plane, and the J omega axis. Everything, every pole in the left-hand half plane means it's a stable system. Any pole, so the difference between every and any there, got to highlight, any pole in the right-hand half plane means that you have an unstable system. And if you have all poles to the left-hand half plane, except for one or two on the J omega axis, it is considered a marginally stable system, because to determine the stability of the system, I actually need to know what the input is. Okay. So that's where we talk about marginally stable, because it could be stable or it could not be stable. And the example is if you have a pole at S equals 0, that's an integrator. Well, if I hit a system with an integrator in it and I hit it with DC, that integrator is eventually just going to blow up and become an unstable system. And this is when we started to really focus in on the fact that you always have the same number of poles as zeros. And normally you have more finite poles. So the poles in the actual transfer function, you normally have more finite poles than you have finite zeros. And so the fact is we have to have the same number of poles as zeros. So the difference between the two tells you the number of the poles at S approaches infinity. Meaning if you plug in S approaches infinity, in the denominator, you will eventually get a bunch of zeros there. So we always had the same number of poles and zeros. First order system, so now we're starting to look at time domain response, but living in the Laplace domain. So all these equations here are just using some variables based on some equations in the Laplace domain, and we can calculate what our time constant is. So if we know what the polar zero is, it's a first order pole, then we can get the time constant. And we know it takes 3 to 7 time constants to reach a steady state. Then we developed the concept of rise time, where rise time was just based again on that pole and this equation here, 2.2, divided by that. And then a 2% settling time means it takes about 4 time constants to get to steady state, right? Because if we multiply this by 4, we get that equation. So first order circuits are pretty simple to analyze. Second order circuits are much more complicated because they have complex numbers and they need a lot more math. And so we developed the concept of a damping coefficient, zeta. We also developed the concept of omega sub n, which is the natural frequency, and omega sub d, which was the damped frequency of a system. And so for a second order system, you always had to have an underdamped system because there is not sufficient resistance, and it doesn't have to be electrical resistance. It could be mechanical resistance or anything like that. But there has to be sufficient resistance to go ahead and make sure that the system doesn't overshoot. If there is insufficient resistance, then you actually have some overshoot. You have some ringing in the system. And that's because when you take the quadratic equation and you do your determining your roots, you end up with complex conjugate pairs. So we wrote things generically as s squared plus 2 zeta omega sub n plus omega sub n squared. And when we did that, we could calculate the percent overshoot, how much it's going to overshoot its steady state value, how long it takes to reach its peak value, and how long it's going to take to settle down. These two equations are exactly the same. It's just that A equals zeta omega sub n. So if you were to do the quadratic equation, you'd recognize that the real part is that zeta omega sub n. And we'll see why in a little bit, why that makes sense. But being able to do and understand this really allows you to pick some design parameters or specify some design things based on, I want to have these performance criteria. Some block diagram math. So moving pickoff points in front of or behind blocks, or moving moving points excuse me, moving points or moving summing junctions in front of or behind points. It really is just here. And the reason, again, is when we have a block diagram of a system, that can be a very complicated system. We're trying to either get the open loop gain or the closed loop gain of a system. So we need to combine those blocks into very simple basic blocks. And so this is the math to go ahead and convert those way more complicated systems into much easier systems. So again, you got to look at a problem and then you got to figure out, all right, I want to put these in cascade. Over here, I want to combine blocks. Over here, I want to move the pickoff point downstream of a gain. So for whatever reason, I need to do that. You can see that I move that over here. So I have to divide by G. Over here, I'm moving it in front. I have to multiply by G. In my summing junction, I'm moving the gain in front over here. So now I can see that I've got to multiply both of those by G. Or if I'm moving in the other direction, I need to divide by my value of G. So again, just looking at combining these blocks, figuring out what's the best way to do it, and then using the items here in the table to help you with that. Then we did Routh-Hurwitz, and when we introduced Routh-Hurwitz, the question was, why bother? Why do Routh-Hurwitz at all? Because I can use my calculator, I can use MATLAB to give me the roots. Well, you can't use your calculator or MATLAB if you have coefficients that are undefined. Why are they undefined? Because your boss has asked you to develop or pick a value of gain, because you're going to have to adjust some linkage or something like that to go ahead and make the system stable. So Routh-Hurwitz is a way to figure out if your system is stable with having some variables in there. And so what's the approach? You start off with your denominator of your characteristic equation. Characteristic equation is the denominator of the closed loop transfer function. Then you start defining your rows with your highest order S term, work all the way down. Then you start to alternate your coefficients. So your first row is your highest order S term, then you skip, then you go to your next order S term, then you skip that term, and then you go on and on and on until you run out. And then your next row, which is S to the -1 from the previous one, you do the same process, but now you pick those elements or those coefficients that you skipped, and then you build from here. And then it literally is -1 over A, I'll call it previous. And then the determinant, A, B, C, D, D, not B. You get the determinant by the previous two rows. This is always going to be in the first column, and this is the column to the right of the previous two rows. Okay? And that is the general form for that. Now, you start building until you get to the S0 row. And remember, our S0 row was always equal to our last coefficient in our polynomial. And our polynomial is the characteristic equation, right? And if you had any sign changes in there, then you had unstable. I mean, you had this number of sign changes tells you the number of poles in the right-hand half plane. So if you have no sign changes, and technically 0 is not a sign change, then you could help define your values of K. The problem with Routh-Hurwitz is sometimes we terminate unexpectedly. If you have a 0 in the first column only, then whenever you do this over here, 1 divided by 0 is going to be infinity. So that's when we substituted in the little value of E. If you had an entire row of zeros, then you had to use the auxiliary equation, which means go one equation up, grab the coefficients from there, take the derivative of that, and continue processing. The auxiliary equation also tells you the j omega axis crossings as well. Okay. This is, you should always check number 1 here before you move to item number 2. If you have a full row of zeros, you don't do the little E approach. So check to make sure you have a row of zeros or not before you substitute the value of E. Steady state error was again another nice way to say, I want to go ahead and calculate what my error is going to be as time goes to infinity, but I don't want to go back and do partial fraction expansion and take everything to the time domain and let t approach infinity. No, I can go ahead and I can directly get that from my Laplace domain coefficients. And so what we take advantage of is the final value theorem, which says as the limit as s approaches 0 of s times whatever equation you have, that is going to be equal to the final value. And so when we calculated steady state error, we normally did it with our value of h being equal to 1. And so we just use, sorry, I keep clearing my throat. I still am dealing with a cold. I apologize. That's the open loop gain, G times H. So we just define the limit as S approaches 0, G times H, as our position constant. If I take the derivative of position, I get velocity, or if I multiply the open loop gain by S, I'm doing the same thing as taking the first derivative. So that becomes a velocity constant. And then taking the derivative of velocity is acceleration. So again, multiplying that by S, I get those terms. These are the P, case of P, case of B, and case of A, which I can use to figure out my steady state error. So the way to tackle these problems is to figure out the system type. The system type tells you number of S's in the characteristic equation at S equals 0. So if it's S, if you factor out an S at the beginning, that's a type 1 system. If you factor out 2 S's, that's a type 2 system. That tells you the number of roots at S equals 0, or it also tells you the number of integrators in a system. And then you just plug it in over here. So once you figure out it's a type 1 system, all I need to do is use this column to tell me what is my constant going to be. Well, I can see that K sub P is going to be equal to infinity. I don't need to calculate it. And my steady state error is going to be 0. I don't have to do any work. So if I give you a type 1 system and I give you a step input, you can go to the table and say, my position constant is infinity and my error is equal to 0. You have no work to do. If it's a ramp input, now you're going to go ahead and calculate K sub V, right? Using our equation, K sub V equals S times my open loop gain, and taking the limit of that as S approaches 0. And then my steady state error is just 1 over that value. If I said, what is the steady state error for a parabolic input? You don't have to do any calculations. You know that my K sub A term is going to be equal to 0, and my steady state error is going to be equal to infinity. Okay. So again, the key thing there is figuring out what system type is, and then using the table to calculate what you need. If we do have an H value that is not 1, then you don't get the actual steady state error. You get this actuating signal steady state error. So it's just a terminology definition type thing. And then our final topic, even though we didn't do a little bit of stuff on Bode plots, but this is just the final exam review. It's not the overall course review, it's just the final exam. But we did some polar and rectangular math. If we do everything in complex numbers, M1 at an angle of theta 1 times M2 at an angle of theta 2, you get that. If M1 theta 1 divided by M2 theta 2, you get that. So doing things with complex numbers is really easy. And since S, our Laplace variable, is the complex representation of frequency, it's equal to j omega, we can get some complex numbers there. So if you're going to solve for complex numbers or solve some math using complex numbers, much easier to do it that way. And what we know is when we did root locus is the characteristic equation has to equal 0 for it to be valid. That allows us to solve for K is equal to -1 over GH. Well, we see if we're looking for the value of K is a real number only. So since this is real, I can't have any angle in here. It has to be equal to a real number. So that's why I just do the magnitude. 1 over the magnitude of GH is that value. Now we start doing our rules. Root locus start and end points. Start at a pole, end at a 0. Start at a pole, end at a 0. Since we always have more poles than 0 finite poles than finite zeros, we always start at a finite pole, but we can end at a 0 that is out at infinity. So, we need to think about that in terms of doing that. And then we do some root locus calculations. So we have sigma A, which is the location of where our asymptotes are, the angles of our asymptotes. Sigma A is going to be the location or the centroid of where those asymptotes take off. And if you're trying to figure out any break-in or breakaway points from the real axis, then you got to take the partial derivative of this equation here. Set that equal to S. But again, you don't have to calculate this or this or this. Why? Because I've had the same number of finite poles and zeros. I have no asymptotes. So I wouldn't do these two if the number of poles equal the number of, not number, but equal. See if I can write that better. So the number of poles, and I'll put finite underneath. If that equals a number of zeros that are finite, you don't need to do these two. There's no reason to calculate theta A and sigma A. If you start at a pole and end at a 0, and you never leave the j omega axis because you're starting at poles and ending at zeros always on the j omega axis, then you don't need to do this one either. The only thing I didn't say in here was on the real axis, right, is the root locus is to the left of an odd pole or 0. And again, those are finite. So what we did when we did root locus, which was kind of really, hopefully a cool experience for you, is because it really takes a lot of knowledge that we've been developing over the last year to be able to solve for, wow, I can actually draw this out using my thought, using what I've learned, the concepts that I've developed. So root locus is really a cool concept because hopefully what you see is, oh my God, I actually have the ability, because I've learned all this stuff, to be able to start to say, I need to do this or I don't need to do this, kind of like you would in the real world. A lot of real world stuff is figuring out, you got a problem here, I need to resolve that problem. What do I need to do to resolve those problems? And how do I resolve them? And so that's kind of how you did root locus. And then we did angles of arrival or departure. So if you have any finite poles or zeros that are away from the real axis, then you can go ahead and calculate those departure angles and whatnot. Also, I forgot to tell you, root loci, where it crosses the j omega axis, you just use your Routh-Hurwitz approach to figure out where you get those. So that's that refinement that you can get. And here are specific test questions. I give you a physical system, find a transfer function, and I'll tell you which transfer function I'm looking for. If I give you a characteristic equation, determine the number of poles in the right-hand half plane, and there's a bunch of ways to do that. If I give you a block diagram, tell me some parameters to meet design criteria. So that tells me right away, I've got some variables in my block diagram that I'm going to need to solve for. Same thing with D, right? If I've given you a characteristic equation, so the first one, the block diagram one, means you got to find the characteristic equation to do that, or find the open loop gain. In the second one, I'm giving you the characteristic equation and asking you to make sure that the system remains stable. Part E, or problem 5, depending on your perspective, I'm asking you to give me a value that meets a desired ESS. I don't want my steady state error to exceed that, so calculating a gain. And then identify regions in the S-plane. So that is, remember that concept here. This was omega sub n. This here was zeta omega sub n. That was the inverse cosine of zeta. Remember how we talked about for second order systems, the 2% is 4 over zeta omega sub n. That's because this is the real one. So being able to understand, hey, I want to settle within 5 seconds or 50 seconds, picking your value of zeta omega sub n. I want to make sure that, for example, I have a percent overshoot that doesn't exceed a certain value. So knowing where in the plot you would pick those, again, as design criteria, that's what we're looking for in that last problem. So that's 8 pages of stuff boiled down into 35 minutes. But hopefully none of this stuff is new, because where's my, oh, there you are. Hopefully none of this stuff is new because it's just a review, right? It's all the stuff that you've done for the semester. So any questions for me? Well, you should all pat yourselves on the back because there's a lot of stuff we've covered, right? A lot of different material, a lot of challenging stuff. But again, I truly believe this class is going to be one of the most useful classes as you move on in your professional careers, not because it's teaching you, you know, and it's not a put down on anything else, not that it's teaching you how to work in teams and write better and all that stuff. It's just that stuff you can learn once you get out in industry because you're expected to do it all the time, right? So being able to write an email that makes sense and is concise is something that you're going to do 50 times a month, for example. So you'll learn to do that because you'll keep doing it. The stuff that we cover in these classes, you may not use it all that often. In fact, hardly ever. But if your supervisor comes up and says, we've got an issue and nobody on our team knows how to do it because you've never seen it before, this gives you the background to be able to go down and say, okay, I need to figure out what the issue is. So what we're covering in here is fundamental foundational material. It's that solid foundation that all of us can stand on and say, okay, I have this basic technical skill and I know these things are true and they have to work because they're physics. They're just, they exist. And so now I can take those and I can apply those to problems and be able to solve, oh, okay, I know this fundamental thing. I can apply this to, you know, hopefully expand my knowledge and then be able to come up with a solution to whatever problem that is occurring. And so why it's so important is because once you have this solid fundamental foundation, you can always go back to the basics and say, what do I need to do to make this work? And that's, you know, that's the hope of these two classes. And that's why this class is so important. Again, kind of going back or calling back to the beginning of the class, the FE exam. What does the FE stand for? Fundamentals of engineering, right? Fundamentals is the foundational, it's the base. It's the important stuff that you build your technical understanding and knowledge off of, these fundamental principles. And so if you've learned a lot and you've done well, then you really need to pat yourselves on the back because this is a lot of fundamental stuff. It's basically 3 years of college, right? With physics and circuits and maybe even some mechanical stuff done in a year. A lot of math too, right? We did a lot of math, so it's pretty broad. And it's not a class that's specific to anyone, like it's not a machines course where you're working on machines all the time. And so you can really delve into machines, but the fundamental stuff that we did here hopefully helps you analyze machines a little bit better, makes it make a lot more sense. So with that being said, I've exhausted all my thoughts. Anything else? Okay. Well, I hope you have a great rest of your day. You have the details about the final, right? We talked about that last time. Let's put it up again one more time, so there's no confusion. I did that last week, or last class, sorry. But let's put it up here. Oop. And again, this is all based on our friends in student records. But if you look at the EET schedule, EET325 is here. So 10:30 to 12:30, right here in this classroom, if you want to come to the live session. And it's a week from Tuesday. So if you want to take the exam online, just let me know. I'll have a video link set up for that class. I just need to set that up. But otherwise than that, you've got the details. You should also be able to see it in your calendar. If you go to Main Street, it should automatically be populated in your calendar. But I think I've already made an announcement for the exam. I believe I have. If not, I will do so after class. So anything else?
Just to make sure, you said a 8.5 by 11 sheet of paper for notes,
Yes. Yep.
double-sided.
Yep.
Perfect.
And I'll bring you like I'll put the Laplace table if you need it. You know, hopefully you need it less and less, right?
Yeah.
But I'll bring those generic big ones there.
Okay. Perfect.
Okay. All right, folks. Have a great day. Enjoy the weather, and I will see you, most of you all on Tuesday. Take care, everyone.
Thank you, Paul.
Thank you.